In this video, we are going to look at an example of a dihybrid cross in which the two parents are not homozygous for either trait or heterozygous for either trait. So let's say we have two individuals, one of whom is heterozygous for the A trait and homozygous recessive for the B trait. We're going to cross that individual with another individual who is heterozygous for both traits. Now we need to produce gametes for both of these individuals, so let's start with the first one. This individual has two different A alleles, so they will produce gametes, one of each having the different A alleles. Since this individual has two of the same B alleles, both gametes will contain the low B allele. Consequently, this individual can only produce two different gametes. The other individual, which is heterozygous for both genes, can produce four different gametes, as we've seen before. One will have both dominant alleles, one will have dominant A and recessive B, a third will have the recessive A and the dominant B, and the fourth will have both recessive alleles. Now, in order to produce a Punnett square here, it's going to be a little different than what we've seen in the past. Punnett squares do not have to be symmetrical. So since we have two gametes for this individual and four gametes for this individual, we are going to have a 2x4 Punnett. We'll put the two gametes from the first individual on the left, and on top we'll put the four gametes from the other individual. Then, following our typical rules of a Punnett square, we just go ahead and fill in all the individuals. Notice that the A's stay with A's and B's stay with B's. That is because alleles that match always go together. Okay, now, we can determine probabilities from this Punnett square as well. So let's look at different probabilities here. Let's say we're interested in finding out the probability of individuals that exhibit both the dominant A phenotype and the dominant B phenotype. We can go to our Punnett square and count those individuals. We have 1, 2, 3 individuals that exhibit that particular phenotype. Consequently, the probability of getting that phenotype in any given birth is 3/8, using the rule of addition. Now let's say we want to find out the probability of getting 3 different births all together in the same family. Let's say we want to find out the probability of getting one individual that has both the dominant traits, one individual that has the dominant A with the recessive B phenotype, and then the third individual that has both recessive phenotypes. Well, we already know the probability of getting one with both the dominant phenotypes, and that individual's probability is 3/8. If we want to find out the probability of getting an individual with the dominant A and the recessive B traits, we just go back to our Punnett square and count. We have 1, 2, 3 individuals with that probability. That would be 3/8 again. Following the same process, we go back to the Punnett square. If we're looking for individuals that show both recessive traits, we can go up here and there's only one individual that shows that. So that probability is 1/8. In order to find out the probability that all 3 of these births happen in the same family, we will use the rule of multiplication. So what we do is we multiply the individual probabilities times each other. So the probability of the first individual, which shows both dominant traits, is 3/8. We'll multiply that times the probability of the individual that shows the dominant A, but the recessive B trait. That probability is 3/8 as well. Then we will multiply times the probability that an individual may have both recessive traits, and that is 1/8. Following multiplication of fraction rules, we take 3 times 3 is 9, times 1 is 9. 8 times 8 is 64, and 64 times 8 is 512. The probability of getting this combination of individuals is therefore 9 out of 512. If you wanted to, you could divide that out into a decimal.